In this chapter, we're going to look at the relationship between energy and matter and how do we approach chemistry from that standpoint. I think I've pointed out in the previous chapter that chemistry is the science of matter and that we would go into more detail into what that actually means in this chapter. So, what is matter? I think I briefly described it as just physical stuff back in chapter 1. So, it's any tangible material, something that has mass, that takes up space. And in chemistry, we kind of focus on what exactly that means in terms of what are the pieces that make it up, how are they organized, and so on. So, as far as chemistry goes, we say that matter is made up of these small particles called atoms. Now, they can be organized into little groups called molecules, and we'll go into more detail into how this happens in a later chapter on chemical bonds. But for now, understand that matter involves these small building blocks called atoms. Okay, so everything is made up of these atoms, right? So uh, like basically how if you could divide matter into smaller and smaller pieces, the smallest piece you could get from a chemistry standpoint is an atom. An atom is a building block of matter in chemistry. Now, it is possible to go to even smaller and smaller pieces. In order to understand how atoms work, we kind of have to do that. So in a later chapter, when we understand what atoms are, we will look at subatomic particles. And if you go into particle physics, you will definitely go into even more detail on this. But as far as we're concerned for chemistry, the smallest practical units are these atoms. So, in addition to matter, we're also going to look at energy. Now, energy is the capacity to do work. In other words, when matter interacts with things, it carries out certain processes. Energy is what's exchanged when these processes happen. Okay, so anytime there's a physical or a chemical change, there's some exchange of energy, this quantity that we call energy. So we'll go into more detail on that later on in this chapter. We'll understand what are physical and chemical changes. Very briefly, we'll go into more detail on that in later chapters, but we'll understand what these physical and chemical changes are and what energy is and how they're related. So let's focus on matter for now. So I pointed out that all physical material in the universe is matter, and we can divide that into certain subcategories. In the previous chapter, in passing, I mentioned pure substances. These are samples of matter where all those pieces making them up are identical. Okay, so if you have a uniform material where all those, that you could divide into these repeating units that are all identical, so to speak, we call that a pure substance. Okay, now if the repeating units are molecules, that substance is called a compound, whereas if all the atoms of your material are identical, we say that that is an element. Okay, when you have more than one substance mixed together, that brings us to mixtures. So let's not get too far ahead. Let's look at each of these in turn. Okay, so starting off with pure substances, if you have for example, a glass of distilled water. Now, if you were to zoom in that sample of water, you would see these repeating water molecules. Okay, so we call that distilled water a pure substance because all of those molecules are identical and there's only those molecules present in the sample. So we have this repeating unit of these water molecules, and that is a pure substance. Now, is that an element or compound? We look at those repeating units, those water molecules, and we see that they're made up of more than one type of atom. A water molecule, so if you're probably familiar with the formula of water as H2O, so a water molecule has one oxygen atom and two hydrogen atoms. So if we were to look at a sort of a cartoon of a water molecule, we'd see an oxygen atom and two hydrogen atoms attached to it. Okay, and the fact that there are different types of atoms within this one water molecule tells you that this is a compound. Okay, a compound contains more than one element making up its molecules. Now, it is possible to get pure substances where all of your repeating units are the same type of atom. So, for example, if you had a bar of 24 karat gold, okay, that bar of gold has only gold atoms in it. It's pure gold. And since gold is an element on your periodic table, we call that sample of 24 karat gold an element. Okay, so the key thing to determine here is that you can't break down an element into any simpler substance through, at least through chemical reactions. Atoms are the simplest building blocks as far as chemistry goes, so we can't break them down further, at least not through simple ordinary chemical reactions. In a compound, though, it is possible to break those molecules into their constituent atoms, into their constituent elements. Now, it's often a little difficult to do this. So, for example, with water, you could separate that into hydrogen gas and oxygen gas if you ran electricity through your sample of water. It's a process called electrolysis. Likewise, there are certain chemical reactions that are able to carry out these sorts of processes. It is possible to split apart a compound into its constituent elements this way. Okay, but my point here is that it's not typically easy to do. You have to use some sort of chemical method. Okay. Now, the other interesting distinction with compounds is that your ratio of elements is always fixed, and that's what how the molecule is defined. So water has the formula H2O because there's two hydrogens for every one oxygen, and that is the ratio that makes water water. If you had a different ratio of hydrogen to oxygen, it would not be water. So in order for it to be water, you have to have that ratio of those elements. Okay, and that's something that's going to be important to keep in mind when we look at mixtures in a second. Okay, another thing that's interesting to note about compounds that help you determine that it's a compound is that the physical and chemical properties of your compound are going to be very different compared to your elements. Let me give you an example here. Sodium chloride, table salt, is NaCl. It's made up of sodium, which is the Na in NaCl. Na is the symbol for sodium. And the Cl is chlorine, okay? And that's what makes the chloride ions in your sodium chloride. Now, if you look at sodium chloride, table salt, I think most of you are probably familiar with it. You've seen it's a white crystalline solid. But compare that to the sodium and the chlorine that it comes from. Okay, sodium metal is a very silvery, soft metal. Okay, and chlorine gas is this sort of greenish yellow, very reactive gas. Okay, those are very, very different from our white crystalline solid, that's sodium chloride, that has a really high melting point. The melting points of sodium metal and chlorine gas are much, much lower than that. I mean, in the case of chlorines, obviously it's lower than room temperature. So that's why it's a gas at room temperature. So my point here is that you can tell that you've got a compound because it looks different than the elements that make it up. That brings us to mixtures. Now, a mixture is when you have more than one substance together. So it's not really a pure substance where there's only one type of substance. You've got multiple substances mixed together, hence the name mixture. Okay. So this mixing process is a physical process. So we'll find that we can separate out the parts of a mixture through a physical process. Okay. For example, you could take a mixture of sand and water and you can filter out the sand, or you could take some salt water and distill off the water. Okay. Now, the other interesting thing here that makes mixtures different is that there isn't any rule as to what ratio you mix your parts of your mixture in. So, for example, if I wanted to make a salt water solution, I could add a little bit of salt and a lot of water, make a very dilute solution, or I could add a lot of salt with relatively little water, make brine, for example. Both of those are mixtures of salt and water, but they're not the same. Okay, so there's no fixed ratio like we see in the fixed ratios of elements making a compound. Okay, so that's a very important distinction to make here. I think this is a common sticking point for a lot of students who get mixed up with why is something a mixture and not a compound, and vice versa. Okay, so here I'll use sodium chloride here as my example of a compound when we want to distinguish things here, right? So, for example, I pointed out that we can separate out the parts of a mixture really easily through some physical process like filtration or distilling and so on. Okay? In the case of a compound, you need a chemical process to do this. You need a chemical reaction or electrolysis. You can do it with electricity, but it's not as simple as just a physical method like filtration. So in the case of sodium chloride, you can't separate out the sodium ions, the sodium atoms from your sodium chloride. You need a chemical reaction to reduce those sodium ions back down to sodium metal. Okay, or you can run electricity through it. You can do electrolysis to get the sodium and chlorine back again. But it's not as simple process but you can't just filter out sodium. Likewise with water, you can't just filter out your hydrogen atoms from those because you've got to break chemical bonds to do this. Okay. The other thing to notice is I think I mentioned the ratios thing already. So in a compound, there's always a fixed ratio of elements, right? So sodium chloride has a 1-to-1 ratio of sodium to chlorine. There's one sodium for every one chlorine. But in the case of a mixture, you can have variable ratios. Okay, so if you make salt water, you can have, it doesn't matter how much salt or how much water you have, you can mix them together. The third way you can distinguish these is by looking at the properties of your mixture or your compound compared to the things making it up. I mentioned that with sodium chloride as a compound is very different from the elements making it up, sodium and chlorine. In the case of a mixture, instead of getting new properties, your mixture kind of has the sum total of your parts of the mixture. So for example, let's say we're looking at salt water. Okay, so you mix salt and water together. The resulting solution you get is still wet like water. It still tastes salty like salt. Okay, so you see where I'm going with this. Like, you kind of get both sets of properties from all the parts of your mixture. Okay. Now, when it comes to mixtures, just as we can distinguish pure substances into elements and compounds, mixtures can also be subdivided into two types. We have what are called homogeneous mixtures and heterogeneous mixtures. Now, homogeneous means same phase. So the prefix there, homo, means same. Okay, that means when you look at that mixture, it looks like it's one material. This is actually where a lot of students do run into that problem of getting compounds and mixtures mixed up. When you look at a homogeneous mixture, just looking at it, it's hard to tell that it's a mixture, that there's more than one thing. It looks almost like a pure substance. Okay, so you've got to watch out for homogeneous mixtures like that. Salt water is an example of this. So if you dissolve salt in water, the salt kind of looks like it's disappearing as it dissolves, right? You only see the water. We'll spend an entire chapter talking about homogeneous mixtures later on in this semester. It's the chapter on solutions, and I'll explain how this happens. But for now, just understand that the key, when you have a homogeneous mixture, it looks like one material. It looks like the majority of that mixture. A heterogeneous mixture, as the name implies, has different parts or different phases. That's what the prefix hetero means different. You can see the different parts of your mixture. So for example, if you have a mixture of sand and water, so you have some muddy water, just looking at it, looking at that cloudiness, you can tell like, okay, there's something in here that's not water. It's not clear, it's not transparent like water should be. There's clearly something in here that's making this cloudy. Okay, so that's an example of that. So if you can see the different parts of your mixture, or at least like tell like visibly that there are different parts, you know it's a heterogeneous mixture. Okay, so here's some examples to keep in mind. So again, like if you know there's more than one substance mixed together and that's a mixture, if looking at that mixture it looks like one uniform thing, then you know it is a homogeneous mixture. So a sugar solution looks like the water making up that solution, even though it's a mixture of sugar and water. 14-karat gold, which is a mixture of copper and gold, looks like gold, right? So it's a homogeneous mixture, even though it's a mixture of two different things. Air is another good example of this. Like air is a homogeneous mixture where you have multiple gases mixed together. Okay, typically with homogeneous mixtures, things are mixed really well. That's another way, by the way, that you can tell that you're dealing with a homogeneous mixture. It's a very even spread of the parts making it up. So for example, with air, you've got about 79% nitrogen and about 20% oxygen, and then a few other gases, right? So they are mixed very evenly. So it's not like when you're in a room, the air feels any different on one side of the room versus the other, right? You don't go to one side of a room and say, oh, it feels like there's more oxygen on this side of the room. No, the air in that room is very evenly mixed, and so it seems like one uniform substance, even though it's made up of multiple gases. Okay. Whereas with heterogeneous mixtures, as I pointed out, usually you can look at it and tell immediately, like, okay, there's more than one thing here. So, for example, if you have oil and vinegar salad dressing, you can see the globules of oil floating around in your vinegar, right? Or vice versa, I guess, depending on which one you have more of in your dressing. Okay. Or like if you've got oatmeal raisin cookies, you can see the raisins in your cookies. Like, it's those are kind of silly examples, but that's my point. With a heterogeneous mixture, you can see that there's something else in there. Yeah, blood and milk are examples of other heterogeneous mixtures. They're mostly water, but clearly they don't look like water. There's obviously other stuff in there that makes them more opaque. Okay, so just to summarize what we've learned here, when it comes to matter, all matter can be subdivided into two main categories. We have pure substances and we have mixtures. Mixtures can be subdivided further into elements or compounds. Okay, where in an element, all of your repeating units are identical atoms, whereas in a compound, your repeating units are identical molecules. And molecules can be split up into their constituent atoms, their constituent elements, using some chemical method or electricity. Okay, so a chemical reaction or electricity can get your compound molecules to be split up into their elemental atoms. Okay. Mixtures can also be subdivided into two categories. We have homogeneous mixtures and heterogeneous mixtures. Okay, homogeneous mixtures look like one uniform material, and that's why they're kind of hard to distinguish from pure substances. So you've got to watch out for that. And then heterogeneous mixtures, you can see the different parts. Now, what distinguishes mixtures from substances? Well, remember, with mixtures, you've got more than one substance together, so that's why it's not a pure substance, but you can separate out a mixture into the pure substances making it up using some physical method. So for example, if we have our saltwater solution, if we distill off the water making that solution, so we boil off the water and condense it, the water you get is pure water, right? So that's a key thing to keep in mind, that mixtures are made up of things that by themselves would be pure substances. It's just that when you mix them together, they, well, become mixtures. Okay, I alluded to properties of matter earlier. Now, what do I mean by properties? Properties are a piece of information that we can pick up about materials, okay, as we look at them or measure them, and this can help us identify. Again, it just tells us information about these substances. Now, there are two types of properties we look at. We have what are called physical properties and chemical properties. Okay, and how we measure them or get information from them is slightly different. Okay, now these properties, as I pointed out, are directly observable. You can measure them, you can observe them. Sometimes it involves the interaction of other substances with your material to notice this. This is especially the case in chemical properties, which I'll get into in a second. Okay, so let's talk about physical properties first. So physical properties are properties of a material. Okay, they're characteristics or information we're getting about a material that can be observed or measured without changing the material. So you can determine a physical property from a substance, and it's still the same substance even after you determine that. Okay. Now this includes things like color or smell or physical state at room temperature, like if it's a solid, liquid, or gas, density. So like for example, like I can look at at a material and say like, oh, that is red, but that doesn't change the material by looking at it, right? So for example, I can look at a bar of iron and say, okay, that's gray in color. But me looking at that bar of iron doesn't change it into something else. It's still iron when I'm done looking at it, right? Now, out of these, melting point and boiling point are also physical properties, and this throws off a few students because you probably are saying to yourself, wait a minute, to determine the melting point, don't I have to melt the thing I'm checking? Isn't that changing it? Isn't it going from solid to liquid? You're changing its physical state, yes, but it's still the same chemical. So for example, if I take a block of ice and I melt it into liquid water to confirm that yes, its melting point is 0 degrees Celsius, it's still made up of water molecules. Whether it's in ice or liquid water form, that's still water molecules making up that substance. So since the water molecules are still water molecules, that is a physical property, not a chemical one. Okay, and same for boiling point. So if I take my liquid water and boil it into steam, and note that the boiling point is 100 degrees Celsius, doing that doesn't make the water molecules stop being water molecules. Okay, so here's an example. So here's a sample of copper. So some physical properties of copper include seeing that it's got this reddish orange color, that copper metal is very shiny. It's a good conductor of heat and electricity. It's got a melting point of 1083 degrees Celsius, so it's a solid at room temperature, and it's got a really high boiling point. These are all things you can observe while the copper is still copper. Okay, so determining that it's shiny doesn't stop it being copper. Running electricity to it or warming it up doesn't stop the copper from being copper. It's still copper even after you pass electricity through it. Okay, so if those are physical properties, a physical change is kind of similar. It's where you're changing a material, but you're not changing the substance making it up. Okay, so it's some change to a material that doesn't alter the atoms or the molecules making up that substance. Okay, now the simple thing here is that there's really only ultimately two scenarios where this applies. You're changing the shape of a material, and or you are changing its state of matter from solid to liquid to gas, or vice versa. Okay, so for example, if I take a sheet of paper and I rip it in half, I've changed the shape of that paper, right? It's no longer the same size. I've got two smaller pieces of paper. But are the pieces of paper still paper? Yeah, they're still paper. So that was a physical change, for example. Okay? So yeah, so changing, like I said, changing shape typically is an example of a physical change. So how you can do that is multiple ways to do that. With metals, metals are very malleable. You can like hammer them into shapes really easily or draw them into wires. That means they're ductile. Liquids can change their shape even though they keep the same volume by changing their container. So that's again a good example of a physical change. If you pour, let's say, water from one container into another, its shape is changing because it's taking up the shape of the container it's in. And of course, as I mentioned earlier, the changing of physical state by melting or boiling, those are also examples of a physical change. Now, to understand what's going on there, let's first talk about solids versus liquids versus gases. There are other states of matter out there, but to be honest with you, these three are kind of the main ones and the only ones we'll focus on in this class. Okay, so in order to distinguish between these three states of matter, the two things I want you to pay attention to are shape and volume. Okay, and ask yourself, are these fixed or variable? A solid has a fixed shape and a fixed volume. Okay, it maintains its shape and volume without anything being done to it. You could leave it alone and it still has the same shape and volume. It doesn't need a container or anything to hold it to that shape and volume. Okay, now a liquid, on the other hand, has a fixed volume, but its shape is variable. Okay, so a liquid can be poured into a container from one container into another, and its shape will change depending on the shape of the container. Okay, that's what I mean by it having a variable shape, not having a fixed shape. However, the volume is fixed. That it doesn't matter what container you pour your liquid into, that sample will keep its same volume. Okay, so for example, if I took a a container, let's say a small beaker of water. Let's say this was like, I fill this up and this has 50 milliliters of water, and I pour it into a larger container. It's different shape, and this is 100 milliliters, let's say. It would take up the shape of its container, but the volume marking would only fill up to the 50 milliliter point. The volume would stay the same. Okay, so that's what I mean by the volume staying fixed, even though the shape would change accordingly. Okay, now that brings us to gases. Gases have neither a fixed shape nor a fixed volume. They will take whatever the shape of whatever container they're in and the volume of whatever container they're in. That's why you're able to it's possible to compress or expand a gas very easily, whereas you can't do that with solids and liquids. Okay. Quick note here about this this tendency of liquids and gases to take the shape of their containers. This is why it's possible to have liquids and gases flow. You can pour them, and this is why both liquids and gases are known as fluids. Right. So you've heard that expression, that word fluid, before. Normally, when you talk about fluids, most people think of liquids. And again, that's kind of the regular English use of the word fluid. In science, in chemistry and physics, when we talk about fluids, we really mean both liquids and gases. Liquids and gases are both considered fluids from a chemistry and physics standpoint. Now, why do we see this? Why do solids have fixed volumes and a fixed volume and shape? Why does a liquid only have a fixed volume but an indefinite shape? And why do gases have neither? Why are they variable for both volume and shape? It comes down to the way those molecules are arranged in those substances. Okay, if you look, let me use water as an example here. So if you have solid water or ice, and you look at the water molecules making up ice crystals, those molecules are arranged in a fixed repeating pattern like this called a crystal structure. We'll talk more about that in a later chapter. But basically, it's this set arrangement of these molecules, the fact that they're held in these fixed positions, that causes them to have that fixed shape and volume. Because they can't really move around very much, they're kind of maintaining that shape and volume of that substance. Now, quick note here about movement. Your water molecules in a solid, or really any molecules that are present in a solid, they're held in roughly fixed position. They might vibrate very gently back and forth, so there is technically some movement in there. As long as you're above absolute zero, your material has some potential energy, and so those molecules are vibrating back and forth very, very gently, but they're not moving a lot. So when I say that they're vibrating in fixed positions, they're roughly staying in the same place. Okay, and that's why solids are solid. Liquids, on the other hand, don't have their molecules set in fixed positions. However, the molecules in your liquid water are still pretty close together. So that's something solids and liquids have in common. Their molecules are relatively close together. The only difference is in a liquid, these molecules aren't held in place. They're constantly sliding past each other, moving around randomly. Okay? And that's the key difference. That's why they can't maintain a shape, right? They have a variable shape, but because they're so close together, and so you can't pull them apart or push them closer, that's what gives them a fixed volume. Okay? Now, gases, on the other hand, have neither a fixed shape nor a fixed volume. The reason for that is, again, the arrangement of those molecules. In a gas, your molecules are very spaced out. They're not held in place, they're constantly moving around, but unlike a liquid where the molecules are all close together, in a gas they're far apart. And it's this distance apart that allows gas molecules to have a variable volume. You can play around with all this empty space that's in between your molecules. You can push those molecules closer together because there's a lot of give there, there's a lot of room to do that, or you can pull them apart and just increase the amount of empty space between them. Okay, there's nothing stopping you there. So that's why gases don't have a fixed volume as well as not having a fixed shape. So I mentioned that change of state from solid to liquid to gas is a physical change. All you're doing is you are just changing the arrangement of those molecules, but those molecules are staying the same. So be ready for recognizing these physical changes or change of state when, and recognizing that they are physical changes. Now, the words that we use to describe these changes are probably familiar to most of you. So when a solid becomes a liquid, we call that melting. When a liquid goes to a solid, we call that freezing, right? Again, probably pretty common words you've heard associated with ice and water. Likewise, when a liquid goes to a gas, we call that boiling, okay, or evaporation. And when a gas becomes a liquid, we call that condensation. Okay. Now, quick note here for those of you who haven't heard these phrases before, and you probably won't get asked about this, but in case you do, or in case you're curious, what do you call it when a solid goes directly to becoming a gas, or a gas goes directly to becoming a solid without going through the liquid phase? Now, you're probably saying to yourself, like, wait a minute, does that actually happen? It actually does. And if you go on to Chem 111 and 112, you'll study phase diagrams and you'll see how this is possible. If you have a high enough pressure, it's possible to do this. But basically, when a solid becomes a gas, that process is known as sublimation. Okay. So an example of this would be carbon dioxide. It's possible to get solid carbon dioxide, what's called dry ice. You may have seen that in packaging for things that need to be kept really cold. So if you go to like a UPS store or something and you want to send someone food, they'll usually pack it in dry ice, for example. Okay. And so your dry ice will go directly to carbon dioxide gas. So we say it sublimes into carbon dioxide gas. Okay. The reverse process, by the way, if a gas becomes a solid directly, that's known as deposition. You deposit a gas as a solid. Okay, so those are physical changes in physical properties, right? Like I said, we're kind of limited in what can happen here because in order for a physical process to happen or a physical change, your material has to chemically be the same before and after the process. That brings us to chemical changes and chemical properties. Chemical properties are ones that that we observe only when a chemical change happens. And for a chemical change to happen, your material needs to change into something else. Okay, so it is now a different chemical compound. Now, and this new chemical, there are signs that this happens. Your new chemical compound will have new physical and possibly chemical properties. And usually there's some things you can observe that tell you that this is going on. Okay, so typically when you see a chemical change, also known as a chemical reaction, like I said, you're changing your material. So you're breaking and reforming new chemical bonds. Okay, so that's what causes one compound to change into another. You're not just rearranging, the atoms, the molecules as they are, but you're actually rearranging the atoms and making new molecules. Okay, so for example, I think I gave you an example of tearing a sheet of paper in half, and now both halves are still paper. That's a physical change. Well, what if I set that paper on fire? When I'm done, I only have ash left. Okay, that ash is different than the paper I started with, right? So that is a chemical change. My burning of paper into ash is a chemical change because the ash is different from the paper I started with. The chemical property there, by the way, is the flammability of the paper. So the ability of the paper to be burned and form ash, that is its chemical property that we observe there. Okay, and again, there are a lot of physical or things you can observe that tell you a chemical reaction is going on. So some of these signs of a chemical reaction, and by the way, you're not going to see all of these at once. You might get more than one of them, but usually it's only a couple of them. So oftentimes there is heat and light being given off, right? There's a change in temperature. A change in temperature that kind of sustains itself, so it's not like when you're melting something you've got to keep on heating it. No, it's like it gives off heat by itself as the chemical reaction is going on. So a good example of this is when you're burning something, right? So during a combustion reaction, so if I burn my paper, it gives off heat and light by itself. I'm not continuously heating it up to burn it, right? It'll continue to burn itself. Sometimes you'll see changes in physical properties. So smell and odor smell and color are physical properties, and the fact that they're changing tells you that you've made something that has these new physical properties. Why does it have new physical properties? Because it's a new substance, right? It's a new chemical substance that you've made. Okay, so a change in smell or a change in color tells you that a chemical change has occurred. Okay, so smell and color by themselves are physical properties, right? If you're looking at something and it's got a particular smell or color, you're observing that, physically. But if you notice something happens and those change, that tells you that that change was a chemical change. Other signs of a chemical reaction are the presence of effervescence, which is just just a fancy word for bubbles. Okay, so if you see bubbles appearing even though you're not boiling the material, that tells you that a chemical change is happening and the product is a gas, or one of the products at least is a gas. And those are the bubbles you're seeing. Okay, so for example, when you drop an Alka-Seltzer tablet into water and it starts bubbling, well, that's an example of a chemical change, right? The Alka-Seltzer tablets are reacting with water, and they're producing carbon dioxide gas. Okay, a precipitate is another sign that a chemical reaction has occurred. If you mix two clear solutions and they turn cloudy, that cloudy stuff is actually a solid, and we call that a precipitate. Okay, so it's any solid that crashes out when you mix together two clear solutions. It's the chemical reaction, the chemical change that's going on between those two solutions that causes the production of that precipitate. Okay, so again, you're not going to see all of these in a given chemical reaction, but the presence of any of them should tip you off that some chemical reaction is happening. Okay, so make a note of that when you're looking at things happening and determining whether it's a physical or a chemical change. Now, we'll spend an entire, or not an entire chapter, but a good chunk of a later chapter talking about chemical reactions. So we'll come back to this in a later chapter, but for now, at least be ready to recognize that something is a chemical change versus a physical change. So let's try a couple of practice problems with this. Okay, feel free to pause this video to give you some time to think about the answers before I give them away. But basically, we're going to look at these three examples here and determine which of these are chemical properties and which of these are physical properties. Okay, so the boiling point of ethyl alcohol is 78 degrees Celsius. Okay, so ethanol or ethyl alcohol, is a liquid and it boils at 78 degrees Celsius. The fact that we're talking about a boiling point should kind of give this away, right? Because remember, any change of state like melting or boiling or whatever is a physical change, and therefore boiling point is a physical property. Okay, the ethyl alcohol is a liquid when you start boiling it. It's a gas when you're done boiling it, but it's still ethanol, right? The chemical molecules making up that liquid and that gas are still the same. A diamond is very hard. Okay, so this is also a physical property, right? Because when you test the hardness on a diamond, you use it to scratch something, for example, or you hit it with a hammer, it's still a diamond before and after you do that, right? So that's why this is just a physical property. Okay, to observe this property, the diamond doesn't stop being a diamond. It's still a diamond. Sugar ferments to form ethyl alcohol. So here we're starting off with one substance, sugar, and we're winding up with another substance, ethyl alcohol or ethanol. Now, these are not different forms of the same thing. It's not like liquid sugar is ethyl alcohol. They're two completely different substances. So this is a chemical change, right, that we're seeing. So this is obviously a chemical property, and that's the ability of sugar to ferment into ethanol. So we could try some practice problems here with physical versus chemical changes as opposed to properties. But again, you're going to approach this very similarly to how we did the practice problems on the previous slide. Okay, so here we're looking for physical and chemical changes. Remember, a physical change is probably the easier one to spot, right? It's either you have a change in shape, of the material you're looking at, but it's still the same material. Or you'll notice words that tend to mark a change of state, like melting or boiling or freezing or evaporating, things like, or condensation, or things like that. So keep that in mind. Okay, so try each of these. Again, feel free to pause the video if you want to give yourself some more think time. Okay, so that first one is melting of snow. Again, the word melting kind of gives that away, right? You're going from solid water into liquid water, so that's a physical change. Now, burning of gasoline. Okay, so think about what's happening to the gasoline there. You start off with, just liquid gasoline, and when you burn it, you don't have to keep on heating it, right? You just give it a spark and it ignites, it catches fire, and it turns into something that's not gasoline anymore, right? It's turning into carbon dioxide and water vapor, which you might not necessarily see, but the fact is it's no longer gasoline when it's done. So that's a chemical change. Now, if you're having trouble like sort of visualizing that, like thinking about, okay, what does gasoline turn into? Don't forget there are certain signs that a chemical change is happening, and so you can kind of look out for those. In this case, the heat and light that you get from the gasoline being on fire, that is a sign of a chemical change. So pretty much anytime you set something on fire, that's a combustion reaction, and a chemical reaction as such. All right, rusting of iron. Is that a chemical or physical change? Now, you think about what that looks like, right? You start off with this nice gray, shiny iron, and it turns into this sort of rusty, like reddish brown, flaky iron oxide. So what's happening there is a chemical change, because your iron's reacting with oxygen in the air to make an iron oxide. Okay, so that's a chemical reaction, a chemical change. And again, just a change in color alone should tip you off that this is a chemical change going on. Okay, so now that we've talked about matter and what it looks like and how we identify properties of it, let's shift over to energy. Now, before we can start discussing energy, I first want to talk a little bit more about temperature. This is a topic that we brought up in the last chapter, and while temperature and heat are not the same thing, heat's a form of energy, temperature is something that we use to gauge how much heat something contains. So even though they're not the same thing, and they're often mistaken to be the same thing, they are related to each other. So we're going to start off by understanding what temperature is. Okay, now I pointed out in the last chapter that while we probably measure things in Fahrenheit, just that's probably the way most of you grew up measuring temperature, and like that's how you tell the temperature of the weather outside. When it comes to science, we're going to use a different scale, actually two different scales. We're going to use the Celsius scale, and we're going to use the Kelvin scale. Now, the Celsius scale is calibrated using water. So the way this is done is it's a very metric approach, I guess, where we kind of set the boiling point of water as 100 degrees Celsius and the freezing point of water as 0 degrees Celsius, and we calibrate our thermometer based on that. We just divide the glass of our thermometer into 100 little increments between the point at which water freezes and the point at which it boils. Okay, and that's basically how you work out the Celsius scale. Now, the Kelvin scale, on the other hand, is just the Celsius scale shifted over by 273 degrees. Now, if you remember back in the previous chapter, I pointed out why we do this. The absolute coldest temperature you can possibly reach, which is called absolute zero, is negative 273 degrees Celsius. So if you set that as 0 on the Kelvin scale, all temperatures are going to be higher than that, right? They're going to be warmer than that. So this is why the Kelvin scale is also known as the absolute scale. Everything's a positive number on that scale. So you just add 273 to whatever your temperature is in Celsius, and that'll give you the temperature in Kelvin. So for example, water freezes at 0 degrees Celsius, that's 273 Kelvin. Water boils at 100 degrees Celsius, that's 373 Kelvin. Okay, so notice that we just add 273 to do our conversion here, which is probably a little counterintuitive. A lot of conversions involve multiplying a number. The Kelvin scale is kind of unique in that you've got to add the conversion factor. Okay. But yeah, so you want to be careful, since the absolute zero is the coldest temperature you can go on the Kelvin scale, you can't have a negative temperature in Kelvin. So if you wind up writing down a negative temperature in Kelvin, you've probably made a mistake somewhere. So that's a quick way to check your work. Okay, so how do we convert from one to the other? Well, I pointed out that we have a difference on the Celsius and Fahrenheit scales. Celsius is calculated or calibrated by looking at what temperature water freezes and boils, but they both are used to measure the temperatures of things. You can still measure the temperature at which water freezes and boils using a Fahrenheit thermometer. You'd get really weird numbers. Water, I believe, freezes at 32 Fahrenheit, 32 degrees Fahrenheit, and boils at 212 degrees Fahrenheit. And and again, that sounds really arbitrary when you compare it to the 0 and 100 on your Celsius scale. But the point is that we can convert from one to the other quite easily. You can see that what's 0 degrees Celsius is 32 Fahrenheit. So there's a 32 degree difference in our starting point there. The other thing to notice is that in the Celsius scale, the difference between freezing and boiling is 100 degrees Celsius. But the difference between freezing and boiling water on the Fahrenheit scale is 180 degrees. So 212 minus 32 is 180. So in other words, the size of a degree Fahrenheit is different from the size of a degree Celsius. So if 180 degrees Fahrenheit covers the same as 100 degrees Celsius, that means that there's 9 degrees Fahrenheit for every 5 degrees Celsius, or 1 degree Celsius is the same as 1.8 degrees Fahrenheit. So if you were looking at the markings on a Celsius thermometer versus the markings on a Fahrenheit thermometer, the markings on a Fahrenheit thermometer would be would be a little bit further apart than the markings on your Celsius. If you were looking at the markings on a Celsius thermometer versus the Fahrenheit thermometer, the markings on your Fahrenheit thermometer would be closer to each other. They'd be closer together because there'd be 2 degrees Fahrenheit, almost 2 degrees Fahrenheit for every degree Celsius marking on your thermometer. Okay, so if you want to visualize that, see both of these thermometers here work the same way. They still have mercury or alcohol in the bulb of the thermometer. There's still a thin glass tube. All that's changing here is just where what the markings are on those glass tubes. So if we have both these thermometers in some ice water, which is at 0 degrees Celsius or 32 Fahrenheit, notice that the mercury or alcohol is at the same level. Okay, but like I said, what that level is called is different depending on the type of thermometer you're using. Okay, so how do we convert from one to the other? If you have the temperature in degrees Celsius and you're trying to convert to Fahrenheit, basically you want to multiply your temperature in Celsius by 1.8, because remember, 1 degree Celsius is equivalent to 1.8 degrees Fahrenheit. Okay. Sometimes you'll see this written as 9/5, depending on who you ask for this formula, but that's written as a decimal. That's 1.8. Now, that helps convert the size of your degrees. Don't forget the starting point is different. So if you want your temperature in Fahrenheit, you have to add 32 then to that answer to get the temperature in Fahrenheit. Okay. So just a little, story time here. I grew up with Celsius, obviously, and to this day I still have trouble trying to convert to Fahrenheit, or when someone tells me the temperature in Fahrenheit, I have trouble visualizing it because I grew up knowing temperatures in Celsius. So it's so I still kind of do this calculation in my head. Well, not exact. I do an approximation of this, where basically if someone gives me the temperature in Fahrenheit, I subtract the temperature 30 degrees from that and divide it by 2, and that gives me a rough approximation of what that temperature is in Celsius. Uh, so I guess if you ever go, let's say, to Canada or someplace that uses Celsius, and they tell you the temperature in Celsius, and you're trying to figure it out in Fahrenheit so that you understand what the numbers mean to you, you would kind of do this in reverse, right? You would basically take that temperature in Celsius, and again, like the rough approximation is you double it and add 30 to it. Okay. Yeah, I can't tell you how many incidents, the little double takes my wife and I have had when telling each other the temperature, especially, in summer when I say like, oh, it's going to be a nice day out. It's going to be like 30 degrees out, and she's like, wait, that's freezing, Anyway, so that's the quick approximation. But let's practice how to do this conversion now. Now you will be given this formula. With at least you'll be given this formula in one direction. So, for example, here you're given the way to calculate the temperature in Fahrenheit from the temperature in Celsius, but not the other way around. So be ready to rearrange this formula to solve for the temperature in Celsius. Now, for those of you who aren't as comfortable with how to rearrange formulas, if you either haven't taken any algebra or you did and you didn't like it that much, don't panic. We'll walk through how to do that. Okay? So let's do a couple of practice problems. So, a person with hypothermia has a body temperature of 34.8 degrees Celsius. What is that temperature in Fahrenheit? Okay, so again, we're given that formula where our temperature in Fahrenheit is 1.8 times the temperature in Celsius plus 32 degrees. Now, the question, going back to the last chapter where I pointed out when you're given a problem like this as a paragraph, and you need to look at this and say, okay, what's the question asking me? What's it giving me? And then how do I come up with a game plan for this? If you're reading this question, a person with hyperthermia has a body temperature of 34.8 degrees Celsius. That's a number that's probably going to be pretty important. What is that same temperature in degrees Fahrenheit? Here are the units of what we want to convert to. We want to go from degrees Celsius. So looking at this formula, the question is giving us degrees Celsius. It wants us to find the temperature in degrees Fahrenheit. So we would plug this number into this formula, okay, into that formula, and go ahead and continue solving it. All right, so let's try that out. So we take our 34.8 and plug it in. So we first do the multiplication. So for those of you who haven't seen this before in math, you generally have to do multiplications and divisions before you can do any additions and subtractions. It's just the order of operations in which you do a calculation. You may know this through some memory device like PEMDAS or Please Excuse My Dear Aunt Sally. So what that stands for is parentheses, exponents, multiplication, division, addition, subtraction. So let me write that down again so we have that down. So PEMDAS, or Please Excuse My Dear Aunt Sally. Okay, so you do things that are in parentheses, right, in brackets. Then you can do things that are exponents, right? So an exponent is where you have a number raised to another number, so like squaring or cubing and so on. Then multiplication and division, and then finally you can do an addition or subtraction. So that's the order you go through here. So we're going to do this multiplication of 1.8 and 34.8 first, which if you do that you get 62.6, and then we're going to add 32 to that. We do that addition, so you wind up with 94.6 degrees Fahrenheit. Okay? Right. Oh, and in case you're wondering why I only went to one decimal place there, since our 34.8 is given to three significant figures, it makes sense to give the answer also to three sig figs. The other numbers in our formula are exact numbers, so they are thought to have an infinite amount of precision, so we don't use that to determine how many sig figs we go to. That being said, again, don't don't stress too much about sig figs here. But if you're curious about why I wrote the answer like that, that's where that came from. Okay, let's try a question, a similar question, but let's go backwards here. So here in this question, they're telling us that we have a temperature of 350 degrees Fahrenheit. What is that temperature in Celsius? So remember, we have a formula where we can, if we're given the temperature in Celsius, we can calculate the temperature in Fahrenheit. But here we're going backwards. Okay, we want to try and rearrange this equation to solve for a different variable. We want to get, in other words, we want to get the temperature in Celsius by itself. Okay, so how do you move things? How do you rearrange an equation? All right, so those of you who haven't seen this before, basically to move something to the opposite side of an equation, you kind of have to do the opposite operator that you're seeing on it. So for example, here we have 1.8 times the temperature in Celsius plus 32. Okay, now the 1.8 and the temperature in Celsius are kind of tied together in these parentheses. Okay, so for the same reason why when you're doing a calculation you kind of do that first, here for moving things you've got to do that last. So first we want to move our 32 to the opposite side. Okay, so since it's plus 32, we subtract 32 to move it to the other side. Here, tell you what, let me do this stepwise so you guys can see how that works. Okay, so if I subtract 32, okay, that cancels it on this side, but I have to write it as subtracting 32 on the left. So I have my temperature in Fahrenheit minus 32, okay, and that's going to equal 1.8 times my temperature in Celsius. Okay. By the way, if you write two variables next to each other like this, and there's no operator, there's no mathematical symbol between them, it's understood to be the same as a multiplication sign, just so you know. Okay, so now remember, I want the temperature in Celsius. I want it by itself. That's what I'm solving for, right? So how do I move my 1.8 to the other side and leave the temperature in Celsius by itself? Well, the opposite of a multiplication is a division, so I've got to divide by 1.8. So I take my temperature in Fahrenheit minus 32 dividing by 1.8, and that will equal my temperature in Celsius by itself. Okay, now you might see me sometimes write this in parentheses just because that shows that this is one term. If you plug this into your calculator without doing this first, you will get the wrong answer, because effectively instead of dividing both these numbers by 1.8, if you just took the temperature in Fahrenheit, divide by 1.8 minus 32, you would only be dividing this term by 1.8. And like I said, it winds up being the wrong answer. So something to keep in mind there. Okay, so let's get move on. Okay, so there's what I've written. So now that we've gotten to this point, now we can just plug in the numbers like we did before. The question tells us the temperature in Fahrenheit is 350, so we would just plug in that number there. We take 350 minus 32, okay, and work that out, divide by 1.8, and that gives us our temperature in Celsius. So you get 176.7 degrees Celsius. That's probably to the wrong number of sig figs, but we'll just ignore that for now. Okay. So that's our temperature in Celsius. Now let's look at the second part of this question. What is that temperature in Kelvin? How do we convert from Celsius to Kelvin? Remember, we've got to add 273 to convert from Celsius to Kelvin, right? Because negative 273 degrees Celsius is 0 Kelvin. So if we add 273 to our answer in degrees Celsius, we get an answer of 449.7 Kelvin. Okay, so that's all you have to do to answer this question. Okay, so keep that in mind that With Celsius to Kelvin, like that last step, it's a little counterintuitive because you're just adding a conversion factor. You're not multiplying or dividing anything. By the way, if you're ever looking at a change in temperature in Celsius or Kelvin, they actually wind up being the same thing. That's because the size of a single degree Kelvin is the same size as a single degree Celsius. You're just shifting your scale. You're not multiplying by a scale, right? It's not like with Celsius and Fahrenheit, where 1.8 degrees Fahrenheit is 1 degree Celsius. Here, a change of 1 degree Celsius is the same as a change of 1 Kelvin. To give you an example from earlier with our water freezing and boiling, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. That's a difference of 100 degrees. If I were to measure that on the Kelvin scale, water freezes at 273 Kelvin and boils at 373 Kelvin. Again, that's a difference of 100 Kelvin. So something to keep in mind if you're ever looking at a change in temperature in Celsius or Kelvin, there it winds up being the same thing. Okay, it's only when you're being asked for what is the actual temperature, then you've got to take your Celsius and add 273 to it. Okay, so let's give you a simple example here. 25 degrees Celsius is standard room temperature. So what is the equivalent of that in Kelvin? So go ahead and add 273 to that, and you figure out that it is 298 Kelvin. Which, by the way, if later on you're wondering why so many problems have a temperature of 298 Kelvin, that's the reason. 25 degrees Celsius is considered standard room temperature. So a lot of problems are done at 298 Kelvin. Okay, so that's temperature. What does this have to do with energy, right? So I mentioned earlier that energy is a capacity to do work. When you have a process happening, there's energy involved, right? Now, that energy can take multiple forms. You have just a whole bunch of different types of energy. You've got chemical energy, you've got nuclear energy, electrical energy, thermal energy, which is heat energy, mechanical energy, gravitational potential energy, etc., etc. There's lots of different kinds of energy out there, okay? That being said, we can break this down into two main categories. You have potential energy, which is energy that's stored somehow, and we have kinetic energy, that's energy associated with motion or movement. Okay, so anytime we have a chemical or physical change, there is energy being exchanged in that process. All right, let me give you an example, right? Let's say you take an object. So let's say you're holding your pen right now to write your notes with, and you lift it up. Okay, now there your muscles are taking their stored chemical energy, and it's doing work, but you're giving that pen gravitational potential energy. You're raising it up against gravity, and by putting it at a higher height, you're giving it gravitational potential energy. When you let go, that pen falls, and that gravitational potential energy is converted into the kinetic energy of the pen falling to the floor. Now, when it hits the floor, that kinetic energy is converted into sound and heat from the friction of the floor and so on. It's lost in certain ways, but that's basically where that energy goes. Okay. To use another example, if you've ever seen a slow motion video of someone taking a slap shot in hockey, I don't know if you've ever done that. We're here in upstate New York, so hopefully most of you have. But basically, if you ever watch it, you'll see that the hockey player doesn't hit the puck itself directly. They hit the ice right before the puck. And if you watch the video of this happening, you'll notice that the stick actually bends backwards when this is going on. What's happening there is you're giving the stick elastic potential energy. It's the same type of energy that you see in, let's say, in a bow, in a bowstring, when you draw an arrow back on a bow. Okay, and similar concept here. But basically, that elastic potential energy then gets converted into kinetic energy when the stick snaps forward and hits the puck. So anyway, my point here is that a lot of these processes involve changes, especially between these two types of energy, potential energy versus kinetic energy. Okay, if you go on to take a physics course, you'll go into way more detail on this, but this is that physics summarized in a nutshell. Okay, now what does this have to do with chemistry, right? How do we apply this to chemistry? Well, when it comes to potential energy, the most common form you're going to see in chemistry is the form that takes the place of chemical bonds. We have energy stored in chemical bonds, and so that's a form of potential energy. When you do chemical reactions, you are breaking and forming bonds. It costs energy to break those bonds. When you form new bonds to make the products of that reaction, you're releasing that chemical energy. Okay? Now, where do we see kinetic energy? Well, I pointed out earlier that molecules move constantly. If you're in a fluid like a liquid or solid, liquid or gas, your molecules are constantly in motion. Even with a solid, where the molecules are held roughly in fixed positions, those molecules are still vibrating a little bit in place. Okay, even though they're roughly in the same spot, they're still vibrating some like back and forth a little bit, and there's some kinetic energy associated with that. Okay, all right. So my point here is that in all the chemical and physical processes we've seen, energy is involved, whether in chemical or potential energy, or whether in potential or kinetic energy. Okay, so how do we measure energy? The SI unit for energy is the joule, right? And the symbol for that is a capital J, right? The other unit you may come across is the calorie. Now, the calorie, which is sometimes abbreviated just cal, C-A-L, is you're not going to see that used too often amongst chemists or physicists, physical scientists, which is kind of odd though, because it is, if you think about how a calorie is measured, it's a very metric unit, right? It's basically it's the amount of energy required to raise 1 gram of water by 1 degree Celsius. Right? That's a very metric way to define a unit. But for some reason, chemists prefer using joules in, like physicists. So it's kind of odd that chemists don't use calories as much. The people who use calories more tend to be biologists or people who work in biology-related fields, like nutritional scientists, for example. Okay. Now, the other reason I think the calorie isn't as popular is, speaking of nutritional scientists, there is another unit that is related to the calorie. I'll get into that in a second. But if you are curious about how to convert from one to the other, 1 calorie is 4.184 joules. Now, I'm going to ask you to remember that conversion. I normally don't ask you to memorize a lot of things, but that is something I want you to memorize, and you'll see why later. Okay. Now, quick note here about joules and calories as SI and metric units. You can use your regular metric prefixes with those. So, for example, a kilojoule is 1,000 joules. A kilocalorie is 1,000 calories. Now, I mentioned that there's a third unit that we kind of use, and this is where things get slightly confusing, and this is probably why calories aren't as popular. And that there is another unit called the nutritional calorie. And it's still spelled calorie, but it's spelled with a capital C. So whether you're abbreviating it with, as cal, or you're writing out the whole word calorie, you're writing it with a capital C. Okay? So it's really unoriginal in that there is another unit that sounds exactly like a previous unit we've discussed. And this is why it's so confusing. One capital C calorie, one nutritional calorie, is equal to 1,000 metric calories. Or, in other words, 1 calorie, capital C calorie, is the equivalent of 1 kilocalorie, 1,000 lowercase c calories. Okay? I agree, it's really dumb, but it's one of those weird things you've got to watch out for. Okay, so this is why I think if you go beyond this class, you'll notice a lot of the measurements that you're going to come across are going to be in joules and kilojoules and stuff like that, that we don't tend to use calories very often. But that being said, in this class, we will use both joules and calories because, since this is a very introductory course, a lot of you are going off into fields where you may need calories. So hopefully, just again, pay attention to whether or not calorie is written with a capital C or a lowercase c. Okay, now I think most of you, when you think of calories, usually think of food. I mentioned that it's very popular with nutritional scientists. Again, because you can describe energy, in this case, energy from food, in terms of these energy units, calories. You can still use joules for these as well. And so, again, notice that we can convert from one to the other accordingly, right? Remember, 1 calorie is 4.184 joules. So if you want to convert from kilocalories to kilojoules, you just multiply by 4.184. These have been rounded off, so it's slightly off there, but that's basically what we're doing here. All right, so let's practice one of those conversions. Let's say we have 150 joules of heat energy that can be provided, chemical energy that can be provided from a pat of butter as it metabolizes, right? As it's digested, it releases 150 joules of energy. How many calories is this equivalent to? Okay, so again, if you are looking at a problem like this, you're reading this out loud, and you think to yourself, okay, what's important in this problem? So if I'm reading this, I say, how many calories? Okay, I know immediately now that's what the question's asking me for, right? There's how many, that should give that away. So I know I'm solving for calories when I do this problem. Are obtained from a pat of butter if it provides 150 joules of energy. So that's our starting point, right? We're starting off with 150 joules, and we want to convert to calories. So we need some conversion factor that's going to tie together joules and calories. Okay, so think back to that equality I had earlier where 1 calorie is equal to 4.184 joules. Okay, so that equality is the important one. So when we're setting this up, remember, we want joules to cancel out, so we're going to put joules on the bottom of that conversion factor. We want our answer in calories, so we're going to put calories on the numerator of that conversion factor. So that's why 1 calorie goes on top, 4.184 joules goes on the bottom. That gets joules and joules to cancel out, and we're left with calories. So mathematically, when you plug this into your calculator, 150 times 1, which is still 150, divided by 4.184 gives us 36 to 2 sig figs. Okay, so you might get a longer decimal than that, but they've rounded off to 36 here. Okay, so I mentioned that heat and temperature are often mistaken for each other, and they're not the same thing, but they are tied together. How are they tied together? Well, one way that they're tied together is through specific heat capacity. All right? When an object absorbs heat or releases heat, its temperature will change accordingly, right? So a material's temperature will generally go up as it absorbs heat. A material's temperature will go down as it releases heat. Now, the rate at which a material does this varies from material to material. Some materials will gain some heat and rise in temperature really quickly, whereas some don't. Their temperature changes really slowly, even though they get the same amount of heat. Let me give you an example here. If you go to the beach, think about going to the beach on a very hot day. If you stand on the sand, your feet get really uncomfortable, right? They feel like they start burning because the sand is so hot. But then you step into the water and your feet feel cold because the water's so cold. But you've got the same amount of sunshine on both the sand and the water, right? It's the same sunlight that's shining on both of those things. And so why is the water so cold but the sand so hot? And the answer is that water has a higher specific heat capacity compared to the sand. So a similar example here is if we gave 4.184 joules of heat to a gram of water, the water's temperature would rise by 1 degree Celsius. So if you were doing this at room temperature, if you had 25 degrees Celsius water, if you gave it 4.184 joules of heat, the temperature would rise to 26 degrees Celsius. However, if you did the same thing with the same mass but of gold, the temperature would rise by 32 degrees Celsius, much more significantly higher. Okay, so if you had your gold at room temperature at 25 degrees Celsius and you gave it that same amount of heat, its temperature would rise up to 57 degrees Celsius as opposed to 26. Okay, so that's something to keep in mind. And the thing that controls this, the property of the material that controls this, is what we call specific heat capacity. Okay. Okay, so if we were to define this, we would see that we're relating together the amount of heat, sometimes represented with the letter Q. We're taking the amount of heat, we're dividing it by the mass of the material in question, and the change in temperature, because that's what this heat's going to do. It's going into raising or lowering the temperature. So when it comes to values of specific heat capacity, which is represented with the lowercase letter c, you can get it in units of joules per gram degree Celsius or calories per gram degree Celsius, depending on what you're using for your units of heat. Okay, now a little note here about what we use specific heat capacity for. This makes the assumption that your material is not going to undergo a physical change. So your material has to stay the same phase. So you can only use it for a material heating and cooling. You can't use specific heat calculations for a change in phase, like for melting or boiling and so on. We'll do more problems on that. We'll get into that concept in a little bit later on in this PowerPoint. Okay, so here's some examples of specific heats, some specific heat capacities. You don't have to memorize this, by the way. The only one you do have to remember is for that of liquid water. And this is where things are really convenient, but the specific heat capacity of liquid water is 4.184 joules per gram degree Celsius, which is the number I asked you to memorize. Okay, so again, that makes sense because it would also be 1 calorie per gram degree Celsius. So 4.184 joules is equivalent to 1 calorie. Okay, so units to watch out for. So I pointed out that your units of specific heat capacity, which has the symbol C, is in joules per gram degree Celsius or calories per gram degree Celsius, depending on what you use for your units of heat. Now, the formula for this calculation, and this formula is given to you, by the way, usually on a quiz or exam, you'll usually find this on your formula sheet, but Q is equal to mc delta T. Okay, now what does that mean? All right, well, Q is the amount of heat energy in joules or calories. Okay, our M stands for mass, and so that's the mass in grams usually. Actually, it pretty much always is, and that's why we get grams in our units. Okay, and delta T is a change in temperature. So the Greek letter delta, it's the thing that looks like this triangle over here. Okay, this triangle is actually the Greek letter delta. It's like kind of the equivalent of a capital D if you were speaking Greek. Okay, so delta T here is 1 unit, by the way. So this is 1 variable. Okay, so you have M, C, and delta T. Delta T is a change in temperature. So typically it's written in degrees Celsius, but keep in mind, by the way, a change in temperature in degrees Celsius is the same as a change in temperature in Kelvin. So it is possible, you may see this sometimes written with Kelvin instead of degrees Celsius. Okay, and if you do happen to see it written that way, that's okay. Okay, so like I said, the amount of the substance is important, the change in temperature of the substance is important. One thing that you might get out of determining your specific heat is that it can also tell you the identity of your substance. So, or vice versa, if you know what material you're dealing with and you look it up in a table, so actually if you go back a couple of slides, if you have a table like this, you can look up the specific heat capacity for a particular material you're dealing with. Actually, while we're at it, make a note of the specific heat capacity of iron. We're going to do a practice problem later on that involves iron, so I'm just telling you this now so you can write it down rather than having to come back to this slide. Okay, so if you have that formula, Q is equal to mc delta T, you can solve for any one of those variables. That being said, sometimes you have simpler problems where you're just looking at the relationship between things. So your heat is going to be directly proportional to each of those other variables because they're on the opposite side of the equation. So for example, if you have a material and you're using the same material, so it's the same mass and the same specific heat, if you double the amount of heat that you give it, the temperature will rise by double the amount. Okay, so again, that's because your change in temperature and your heat are directly proportional to each other. They're on opposite sides of this equation. So something to keep in mind if you ever have a problem that's qualitative. You don't have to treat this like a math problem. It can be more like a logic problem. Okay, other point that I need to make here based on the fact that your change in temperature and heat are related to each other, and that has to do with the sign. Okay, whenever we talk about a change in anything, so if you ever see delta something, okay, it's always the final state minus the initial state. So if you have a rise in temperature, your final temperature is going to be hotter than your initial temperature, so delta T will be a positive number. Well, if mass is a positive number, which mass always is, and your specific heat is always a positive number, okay, what is your heat going to be? Well, it will also be a positive number. Okay, so that's something to keep in mind. But what if your temperature is cooling? What if your object cools down and therefore your final temperature is lower than your initial temperature? Well, remember, a small number minus a large number gives you a negative delta T. So that means that Q, if your delta T is negative, Q will also be negative. Okay, so depending on the sign on Q, that tells you something about whether your substance is gaining or losing heat. Okay, so keep that in mind, especially later on when we get to heat transfer problems in a little bit. So if something has a negative value for Q, that means it's losing that heat, it's giving out that heat, and that's why its temperature is dropping. Okay. Oh, a quick note here about how this is written out in this PowerPoint. I've used SH here for specific heat. Normally I would use the symbol C for specific heat. That's what almost everything uses as the symbol for specific heat. For those of you who have the old Timberlake textbook, for some reason Karen Timberlake uses SH for specific heat instead of the letter C. I'm not sure why she does that. She's literally the only person I've ever seen do that. But for those of you who do happen to have that textbook, I left this reference in there. So in case you're wondering about that. Okay, so how do we convert things? Let's try some problems out. Okay, so before we begin, I'm going to start off with this very simple, silly conversion like we did earlier with our pat of butter and 150 joules. You have a can of Pepsi 1, okay, and it has 1 calorie. I think the concept of Pepsi 1 is probably way before most of your times, but it was something that Pepsi marketed very, very briefly. Anyway, so it contains 1 capital C calorie, a nutritional calorie. How many joules of heat is that? Or how many joules of energy is that? And I know this is a silly starting off problem. I'm going to use this number to do a later calculation. Okay, so feel free to pause this here, but think about how you would set this up. We're starting with 1 calorie, 1 capital C calorie, that's our starting point, and we want to set this up so that we wind up with joules at the end. Okay, so you want to probably find some conversion factor between capital C calories to joules. Now, There isn't a direct way to do this, but the middleman here might be a lowercase c calorie. So ask yourself, how many calories, lowercase c calories, are in one nutritional calorie? Okay, if you've forgotten, it's 1,000. Okay, so one nutritional calorie with a capital C is equal to 1,000 metric calories. And then we need to convert between metric calories and joules. So think about how we do that. What's the conversion factor for that? Okay, it's a number I asked you to memorize. So ask yourself, do I multiply or divide by 4.184? So if you're not sure how to multiply or divide, again, watch your units here and make sure you're setting up your conversion factors so that the units in one step cancel out in the next step. So we're starting off with calories with a capital C, so we know we want to divide by calories with a capital C in the next step. So we have one nutritional calorie on the bottom, and we have 1,000 metric calories on the top. Okay, and that gets calories with a capital C to cancel out. Now in the next step, we want lowercase c calories to cancel out. So we want calories on the denominator on the bottom, and we want joules on top because that's where we want our answer in. So again, lowercase c calories will cancel out. So we have our 4.184 joules on top, our 1 calorie on the bottom. And again, notice that our units have canceled out, and we're left with just joules. So when we plug these numbers in, if I take 1 times 1,000 times 4.184, divide by 1, which is the same number, you get 4,184 joules. Okay, so that was just a little practice problem to make sure you're getting the hang of these conversions. Let's use that answer to do the next couple of problems. So if we have 4,184 joules, okay, and we want to use that, let's say we convert that completely into heat energy, how much water can we heat up? So let's say we've got water at 0 degrees Celsius, and we're heating it up until the point it's boiling. Now remember, boiling is 100 degrees Celsius, right? So think about what this question is giving you and what it's asking you for. The question tells you we have 4,184 joules. We're being asked how many grams of water. So that's going to be our ending point. We want to get to grams. And we're told that the water goes from 0 degrees Celsius to boiling. So there's a change in temperature here. We're going from 0 to 100 degrees Celsius, which is a difference of 100 degrees Celsius. So something to keep in mind, that delta T is going to equal 100 degrees Celsius. Okay, so with that in mind, you could either set this up like you would with any other conversion factors using a table, but I'm guessing most of you would probably like that old formula, Q is equal to MC delta T. Okay, so if we rearrange that, you would get this value. Let me show you how that's done. For those of you who are still getting the hang of rearranging formulas using algebra, let me show you how to do that, to get Q, to go from Q is equal to MC delta T to getting this version that they've got here. Oops, let's want to get rid of the pen here. Okay, there we go. So we are starting off with Q is equal to MC delta T, right? And we want the mass by itself, because we're solving for how many grams, and grams is a unit of mass. So we want mass by itself, so we need to move C and delta T to the other side. Now, remember, when variables are just written next to each other and there's no multiplier, it's automatically assumed that the operator is a multiplication symbol. Okay? So what's the opposite of multiplication? Well, division, which in this case is shown with a with the quotient, with the line that you see in a fraction. So we move C and delta T, we divide those under Q. Okay, so that's why they're written on the denominator of this fraction. Okay. By the way, it's you could treat this, if it's easier, you could treat this as one thing, Q, C and delta T as one unit that we just
divide by the whole thing. And that's why there's still a multiplication sign here, because they're both on the denominator, but they're multiplied by each other. Okay, so anyway, we can do it that way, or we can plug in and set this up like we would any conversion factor problem. So we start off with 4,184 joules, and so that's our Q, right? So we divide by C, which if you do that, you'll notice that to divide by something, that's the same thing as writing the inverse of it. So if the specific heat capacity of water is 4.184 joules per gram degree Celsius, so let's write that out. Okay, so C for water is equal to 4.184 joules per gram degree Celsius. What that means is that's 4.184 joules for divided by 1 gram times 1 degree Celsius. So if we were to divide by C, what that means is that fraction gets flipped. Okay, so if you were to extend this out and say, all right, that's the same as times 1 gram times 1 degree Celsius, if I'm dividing by this, I'm just flipping this. And that's kind of how it's written here. We put the 4.184 joules on the bottom, 1 gram and 1 degree Celsius on top, and notice that gets joules to cancel out. Okay? Now, notice that we're also dividing by delta T. And remember, delta T is 100 degrees Celsius, so we divide by 100 degrees Celsius, and that gets degrees Celsius to cancel out. Now notice that the only unit we have left is our grams over here, which is a good thing because that's what we want our answer in. So if we plug this into our calculator, 4,184 times 1 times 1 divided by 4.184 and also divide by 100. Okay, or you could multiply 4.184 times 100 first and then take 4,184 divided by that answer. You'll get the same thing, which is 10 grams. Okay, so there's 10 grams of water. That's how much water we could heat up with 4,184 joules. Now, let's try a similar problem. Okay, so let's say we still had 4,184 joules of heat energy we're using to warm up some water. Let's say instead of starting off at 0 degrees Celsius, we're starting off at 25 degrees Celsius. So very similar problem. How many grams of water can you heat up with this much heat energy, with this 4,184 joules? Okay, you're going to set this up very similarly to the previous problem. So feel free to pause this video and then continue on as I explain how this is done. So we're still solving for grams, and we're still starting with 4,184 joules. The only difference here is going to be delta T, because this is still water, so your specific heat is still 4.184 joules per gram degree Celsius. That number has not changed. So the only other variable that's left is delta T, and notice that delta T involves your water starting out going from 25 degrees Celsius to 100. That's the difference of 75 degrees Celsius, which is different from your 100 degrees Celsius in the previous problem. So we're setting it up the same way. Q is equal to C divided by delta T, or M is equal to Q divided by C and delta T. So we would plug these into our problem the same way. We take our 4,184 joules, divide by C to get joules cancel out, divide by 75 degrees Celsius, get degrees Celsius to cancel out, and we'd get our answer in joules, or in our answer in grams, sorry. Okay, so you should wind up with about 13.33 grams. Again, probably not the perfect number of sig figs, but close enough. Okay, why don't you guys try another problem, very similar, but here we're going to solve for something different. So here, we've got 50 joules of heat. We're applying it to 10 grams of iron, and how much will the iron warm up? Okay, so in other words, what is delta T for this thing of iron? Okay. So when you do a problem like this, you want to, again, you want to kind of set it up the same way as before. You're going to read through this and say, all right, what is this question giving me? And what am I solving for? And how do I connect them? So we're starting off with 50 joules of heat. Okay, remember, heat, and especially when you see the units of joules, that is going to be our Q in our equation. We've got 10 grams of iron. So 10 grams, okay, that's a mass, M. By how much will the temperature of the iron increase? So in other words, what is delta T? What's this rise in temperature that we're getting out of our, from heating up this iron? Okay, so if we look at the formula we need, we have Q is equal to mc delta T, and the question wants us to solve for delta T. So how do we get delta T by itself? How do we move M and C to the other side? Okay, so remember, we divide by M and C. Okay, so delta T is equal to Q divided by M and C. Now, notice that the question gives us Q, it gives us M, we're solving for delta T. The question doesn't directly tell us C. Okay, now if this were a quiz or exam, I would tell you the value of C. In this case, since it's a problem that you're not taking on a quiz or exam, you can look that up in the table that was a few slides back. But to jog your memories, your specific heat capacity for iron is 0.45 joules per gram degree Celsius. Okay, so go ahead and plug those numbers in. Take our 50 joules. We divide by the specific heat capacity of 0.45 joules per gram degree Celsius. Again, notice that joules cancels out. And we divide by our 10 grams, get grams to cancel out, and you get your answer in degrees Celsius.
Up until now, we've been looking at a single object gaining or losing heat. What happens when there's a transfer of heat from one thing to another, right? So where does that heat go or come from? So basically, if you take a hot object and a cold object and put them together, the hot object will lose heat and its temperature will drop. The cold object will gain heat and its temperature will rise. Here's the thing. This is what ties them together. The heat, the same amount of heat that's transferred, okay, is uniform. So the same amount of heat your hot object is losing is equal to the amount of heat that your cold object is gaining. Okay, like from a value standpoint, they're the same number. Now, you've got to think back to where we talked about the signs of these amounts of heat. So from the hot object's standpoint, this is going to be a negative value because that object is losing that heat, whereas that will be a positive number for the cold object. But the point still remains that numerically those two things are the same. Now, we can take advantage of this to do what is called calorimetry. In other words, if we take an insulated container and fill it with a material that we know the specific heat capacity of, so water in other words, we can use it to determine information about an unknown as long as we keep track of the change in temperature. Okay, so in this example here, we take a hot object, okay, and we know its mass, we know its initial temperature, okay, and if we know the initial temperature of our water and we drop our hot object into the water, okay, we can keep track of the change in temperature between the two. The water will warm up, your hot object will cool down, and they'll both keep doing this until they reach the same temperature and stop. Now, this is the final temperature for both your water and your metal object. So in other words, if you know their initial temperatures, you can figure out delta T for both of them. You hopefully have already got the mass for both of them, okay? And since you have the specific heat capacity for water, you can figure out how much heat went into the water to raise its temperature. Now, that's going to be a positive value, right? Well, that same value is going to be a negative value
for your hot metal object. Okay, so you now have Q for your metal object, you have the mass, and you have the change in temperature. You can now solve for that specific heat of that unknown object. Back when I taught high school, we actually did a lab like this where we took some paper clips and used that as our hot metal object and dropped into a calorimeter with water. And we were able to figure out the specific heat capacity of the steel making the paper clips. It was actually surprisingly accurate. So coffee cup calorimetry, say that 10 times fast, is a very useful technique for doing some of these problems that involve heat transfer. In fact, when you do your energy and matter lab, we actually will use coffee cup calorimetry to determine, we're going to basically cool down water with some ice, and using a similar method, we're going to figure out the specific heat of fusion for the ice as it melts. Okay, but anyway, I'm getting ahead of myself. Why don't we try a problem where we take a hot object, drop it in water in our calorimeter, and figure out information about that object. So we have a 50-gram sample of tin, and it starts off at 99.8 degrees Celsius. It's dropped into 50 grams of water at 15.6 degrees Celsius. If the final temperature of both the tin and water is 19.8 degrees Celsius, what is the specific heat of the tin? So think about what this question is giving you. It's giving you 50 grams as the mass for the tin. Okay. It's telling you that the tin was initially at 99.8 degrees Celsius. Okay, so that's the final temperature, or sorry, the initial temperature for the tin. Okay. And we're told that we have 50 grams of water, so that's the mass of the water. And the water was initially at 15.6 degrees Celsius, so again, that's the initial temperature of the water. And you're told that the final temperature of both is 19.8 degrees Celsius. Now you're being asked for the specific heat capacity of the tin. What is the specific heat capacity of tin? Now, the question doesn't give this to you, but you should know the specific heat capacity of water. And so that's 4.184 joules per gram degree Celsius. Okay, that's something you should memorize. So, let's keep stock of what we've been given here. Okay, we've been given all these things, and we're trying to solve for the specific heat capacity of the metal. Okay, now they've given us final and initial temperatures. It might be a good idea to go ahead and calculate what your delta T is for each of these. Okay, so for our tin, okay, here we have our tin. Notice that the tin is starting off at 99.8 degrees Celsius, and it's cooling down to 19.8 degrees Celsius. So what's the delta T if we take this final temperature and subtract that initial temperature of 99.8? Well, it's going to be a delta T for our tin of negative 80 degrees Celsius, because remember, our tin's cooling down, that's why this is a negative number. Now, look at your water. You've got a final temperature of 19.8 degrees Celsius and initial temperature of 15.6, so that water temperature rose. You're going to get a positive value here when you take 19.8 and subtract 15.6. So delta T for your water is going to be 4.2 degrees Celsius, positive 4.2 because it's warming up. Okay, so we can break this down into two steps. Look at the information you're given, okay, the one that's more complete, and you'll notice that the water has 3 out of the 4 variables. We've got the mass for the water, we've got the specific heat capacity of the water, and we've got delta T for the water. In other words, if we look at our formula, Q is equal to mc delta T, we have the mass, we have the specific heat, we have delta T for water. We can figure out how much heat went into the water. Now, this amount of heat that went to the water is going to be the same amount of heat that left our tin. So if we have Q for our tin, and we have the mass of tin, and delta T for the tin, we can then solve for specific heat capacity of tin. Okay? So if you want to try this yourselves, again, pause this video, but I will now go ahead and explain how we go about this. So, like I said, you want to start off with your water. Just solve for water. So we know that our water has a mass of 50 grams, a specific heat capacity of 4.184 joules per gram degree Celsius, and we saw that delta T is 4.2 degrees Celsius. So if we multiply those three numbers, grams cancels out, degrees Celsius cancels out, and we're left with a value of around 880 joules. Now, this number is probably rounded off to 2 sig figs because it looks like the temperature was 2 sig figs, so I'm guessing that's why they did that. But anyway, my point is this is the amount of heat that went into the water. So the negative equivalent of this is the amount of heat that left the tin. So if you have the formula Q is equal to mc delta T, oops, and we want to solve for the specific heat capacity of tin, we have to divide by mass and change in temperature. So we take our Q, which is negative 880 joules, and divide by our mass of 50 grams and our change in temperature for tin of negative 80 degrees Celsius. Okay. So if you're having trouble seeing that, Q divided by M and delta T is equal to C by itself. Okay. So when you plug that in, you should get 0.22 joules per gram degree Celsius. Again, you can tell the units are going to be that because we have joules divided by grams in degrees Celsius. And that's going to be our specific heat capacity for our tin. All right, I mentioned earlier that we can only use that formula, Q is equal to mc delta T, when a material stays the same, when it does not change phase from, let's say, solid to liquid or liquid to gas or vice versa, right? So if we want to keep track of that as well, to keep track of phase changes, we can use what's called a heating curve or a cooling curve. Now, these work in the same principle. It's just that with a heating curve, you're adding heat. With a cooling curve, you're removing heat. You're cooling down something. But what we're going to do here is we're going to plot a graph of how the temperature of a material changes. So on the y-axis, we have the temperature. And on the x-axis, we've got heat that we're adding or removing. Okay, so heat's going to be on our x-axis. Temperature is on our y-axis. All right. Now, you're going to notice that the graph will slope in some places and it'll go flat in some other places. So the terms we're going to pay attention to here are specific heat, which we've already covered, but the two flat bits we're going to look at are the heat of fusion and the heat of vaporization. These are the heats that are associated with a change of phase. Heat of fusion is involved with a substance melting or freezing, and the heat of vaporization is involved with a substance boiling or condensing. So let's have an example. Let's look at a generic heating curve here for something. Now, by the way, you can tell this is a heating curve because as we're adding heat, two, notice that the temperature is steadily rising. Okay, so that's a sign that we're adding heat, and so it's a heating curve. If you had a cooling curve, it would look like this, except it would slope downwards. Okay, but it would be kind of similar where you constantly have a slope downwards in some places, you have flat parts in some other places, and yeah, you alternate between them. So what's going on here? Okay, why does this curve have this particular shape? So let's start off by looking at what's going on in this problem. Let's move along this graph in terms of temperature and heat added. So we're starting off here over here on the left. We haven't added any heat yet. You're at a particular temperature. Okay, so let's say we have a solid that is really cold. It's so cold it's at a temperature below its melting point. So if we have a solid that's at a temperature below its melting point, what happens when you heat it? Now, your natural instinct is probably to shout out, oh, it melts. You be careful of what I said right there. It's below its melting point. Okay, so to give you an example here, if you had ice at negative 20 degrees Celsius and you gave it some heat, it wouldn't melt because ice needs to be at 0 degrees Celsius in order to melt. Okay, so your solid here does not melt because it is below its melting point. So when you add heat to this solid, that heat goes into raising its temperature. And that, by the way, is why the graph slopes up over here. As you add more and more heat, the temperature starts rising, following that formula Q is equal to mc delta T. And then you get to this point here. Now you're at the melting point. So what happens when you continue to add heat to a substance that is at its melting point? Well, that heat goes into melting the material. But if it's going to melting the material, that means it's not going into changing its temperature using specific heat capacity. And that, by the way, is why this graph flatlines while it melts. Okay, so you start off over here with your solid that started to melt. By the time you have added this heat over here, you now have a liquid at that same temperature. In between, you have a mixture of solid and liquid. So, for example, if you had ice water that was where the ice and the water were in equilibrium with each other, the temperature of that mixture would be 0 degrees Celsius exactly. Okay. Now, once all of your solid has melted into its liquid, and you keep on adding heat, that liquid's going to start warming up. Again, following Q is equal to mc delta T. It'll keep on warming up until you get to its boiling point. Now, just like with the melting point, once you're at the boiling point, the heat you add is going to go into boiling your material. So you start off with something that's all liquid, and you start heating it, and now you start getting a mixture of liquid and gas until finally everything's been converted into a gas. Now, at this point, if everything's already gas, no more energy needs to go into changing it into a gas because it's already a gas. The rest of that energy goes into raising the temperature of the gas. And again, that's the slopey bit of this graph here, where you can use Q is equal to mc delta T if you have the specific heat capacity of the gas. Okay, so notice that there's no temperature change in those two flat parts where we have a phase change, where our solid becomes a liquid and our liquid becomes a gas. Okay, so because these parts of the graph are flat, you can't use Q is equal to mc delta T to do any calculations here, because delta T is 0. You'd be multiplying by 0, so it doesn't make any sense. Instead, what you need is the heat of fusion, which is the heat associated with melting, and the heat of vaporization, which is the heat that's associated with boiling. Now, these values are given in units of joules per gram. So you might get them in other units as well. For example, joules per mole. We haven't talked about what moles are. We'll learn about that in a different chapter. But my point is that it's a particular unit of energy per unit of amount, whether that amount is mass or some other way of counting it. So for now, we're just going to have the heat of fusion be 334 joules per gram. Now, you don't have to memorize that number on a quiz or exam that'd be provided to you, and otherwise you could look it up here. Okay, so what does that mean, right? It means that 1 gram of ice needs 334 joules of heat energy to melt completely into water. Okay, now please note this is this heat of fusion for water only. This does not apply to other materials. Okay, so yeah, so that's basically what you would use this for. So if you have the mass of your ice in grams, you multiply by 334 joules per grams, and that'll give you the amount of heat energy required to melt it in joules. Okay, so let's try a problem that involves a heating curve. Okay, so now there might be more than one thing going on. Let's try reading this problem and see what this question is giving us and how to tackle it, how to break it down. So calculate the heat needed in joules. Okay, so we already know what we're aiming for. We're trying to get joules. To melt 15 grams of ice at 0 degrees Celsius and to heat the water to 75 degrees Celsius. So we know we're starting off with 15 grams of ice at 0 degrees Celsius. Now, notice there are two things going on. If you're reading this, okay, you kind of have to get an eye for this, but basically notice that we are starting off with ice at 0 degrees Celsius and it's becoming water at 75. So there's two things that's changed. Our ice has melted into water, and the temperature has risen from 0 to 75 degrees Celsius. Now, if you're having trouble visualizing this and recognizing, like, oh, I'm going to have to do two things to solve this problem, it sometimes helps to have um, a, a cooling or a heating curve here to help visualize what's going on. Okay, so basically, if you have your heating curve, okay, now here's a big heating curve, and I'm just going to show you on parts of this. If you were trying to sketch this out, you wouldn't have to draw the whole thing. Let's say you just started off over here, and you say, all right, I've got ice at 0 degrees Celsius. That's where I'm starting. I'm starting with 15 grams of that ice. What happens when I heat it? When I heat it, it's going to melt from liquid ice at 0 degrees Celsius into, solid ice at 0 degrees Celsius into liquid water at 0 degrees Celsius. Okay, that's one part of my calculation. I need to figure out the heat that's associated with that. Okay, what's the heat that goes from here to here? Secondly, we're going from liquid water at 0 degrees Celsius to liquid water at 75 degrees Celsius. Now, notice that it's still water during this step, but its temperature is changing, right? Our final temperature is 75 degrees Celsius. Our initial temperature was 0 degrees Celsius. That's a difference of 75 degrees Celsius. So we have a delta T here. And don't forget, if we have 15 grams of ice, we also have 15 grams of water, right? That's what the ice melted into. So we have an M for our sample of water now. Okay, so we have the mass, we have the change in temperature, and because it's water, we also know what C is, 4.184 joules per gram degree Celsius. So you can use that to solve for the heat that's associated with this step. Okay, so the key thing is this question's asking us what is the total amount of heat. So if we're starting here and we're winding up here, what is the amount of heat for this part of the graph? Well, again, there's no way to do that directly. We have to break this down into two steps. We have to figure out, okay, what's the amount of heat for this step, okay, using our heat of fusion, and what's the amount of heat for this step using our specific heat capacity. So break this down into two steps, find the answers for each, and then just add them together. So let's do that first step. We're melting 15 grams of ice into liquid water. Well, ice has a heat of fusion of 334 joules per gram. So if we start off with 15 grams, would we multiply by 334 or divide? Well, you want to multiply it because that way grams cancels out. And you wind up with 5,010 joules of heat energy required to melt that ice. Now again, remember, this is not the final answer. This is just part of the answer. Your 15 grams of liquid water you've made now needs to heat up. So again, think back, if we go back to that graph, you can kind of see that here. We're going from 0 degrees Celsius to 75 degrees Celsius. So that's a delta T of 75. And we have 15 grams of liquid water. So let's set that up. 15 grams times the specific heat capacity of our liquid water times our 75 degrees Celsius. Notice that grams cancels out, degrees Celsius cancels out, and you get your answer in joules. Okay, I've written it up here, 4,710 joules. So, what's the total amount of heat? Just add up those two numbers. So we have 9,720 joules. Okay, let's look at a heat of vaporization and do similar problems. Okay, so like heat of fusion, heat of vaporization also is used to describe 1 gram of a material, in this case 1 gram of water, and we're looking at the amount of heat energy required to boil off that liquid into a gas. Now, notice that this is a very high number. It actually costs a lot of energy to rip apart the water molecules and separate them out into a gas, right, into the gas phase. So it's 2,260 joules per gram is something you want to keep in mind. Now, again, you don't have to memorize this number, but in case you're curious, that's why that number is so much larger than 334. So, similar stopping point. We're going to continue on from where we stopped, and we have water at 75 degrees Celsius. How much heat do we need to convert it into steam at 100 degrees Celsius? Again, notice the difference here, that we are starting with water and we're converting into steam. So there's boiling going on here. Also, we're going from 75 degrees Celsius to 100 degrees Celsius, which I guess they've written over here as well. That's a rise of 25 degrees Celsius, so keep that in mind for our delta T. So again, if you want to visualize this, we're starting off with 75 degrees Celsius, liquid water, and we're warming it to 100 degrees Celsius. So notice that we have a change in temperature, and this is going to use Q is equal to mc delta T to do. Now, we have liquid water at 100 degrees Celsius. We want to convert it into water vapor at 100 degrees Celsius. Okay, so keep in mind that this involves heat of vaporization for our 15 grams of water. So just as before, split this up into two steps. So first calculate the heat that's required to warm up your water, and then calculate the heat that's required to boil off that resulting water. So to show that out, the heating up part is Q is equal to mc delta T. We know that the mass of water is 15 grams. We know C for water is still 4.184 joules per gram degree Celsius. And we know the delta T for water, our change in temperature, if we're going to 100 from 75, that's a rise of 25 degrees Celsius. So get grams to cancel out, degrees Celsius to cancel out, and we multiply those three numbers, we get 1,570. Again, this is not the final answer. We still have to boil off that water. So we have 15 grams of water, and we know that the heat of vaporization is 2,260 joules per gram. So think again about how we're starting off with 15 grams. Would I multiply or divide by this number to get grams to cancel out? Well, remember, since grams is on the denominator, we multiply, and that gets grams to cancel out. So 15 times 2,260 is 33,900 joules. A lot of energy required to boil off all that water. Okay, and remember, your final answer is just those two answers added together. So we take our 1,570 from our warming up of our water, and then the 33,900 joules in order to boil it, and that gives us our total amount of heat for this whole process. Okay, so that's it for this chapter, right? As always, here are some suggested practice problems from the textbook. If you want more practice, we can work on some of the even numbered problems in your textbook that don't have the answers at the end of the chapter. We can do that during our class time. But of course, be ready for a quiz on this material, and and you'll see some of these concepts in the energy and matter lab that we'll do. But as always, if you have any questions, just let me know. And good luck in preparing for your quiz and lab report.